Okay, so let's get started. So, anybody notice something different today? I'm sorry? It's rotated, isn't it? It's a different stage. Yeah. By the way, how many of you know that they can rotate the stage here? Oh, I see. Everybody knows that. Okay. What I didn't know is that the heights of the blackboards are different on the different parts of the stage. So that was okay. So so today we'll talk about power law distributions, which are these are very different kinds of probability distributions than we've seen so far. Okay, and in fact, power law distributions became, these were all the rage about 15 years ago in the 90s, because it was realized that a number of phenomena that we were seeing on the internet, they led to these kinds of distributions, which are very, very different from anything we've seen before in this class. Okay, so they are very different from the kinds of probability distributions you usually study in a statistics class. So let me start with a particular kind of power law distribution called the Zipf distribution. Okay, so how does the Zipf distribution work? So Zipf was, George Kingsley Zipf was a linguist from the early part of the last century. And while analyzing word frequencies used in language, he realized that the most frequently used words were, of course, they tended to be the shortest ones, but also there was a regular pattern in how they were used. So, for example, the most frequently used word in the English language turned out to be the. Okay? And let's say it had a certain frequency. So if you had a corpus of a million words, okay, then let's say that the occurred n times in this corpus. Okay? Well, if you looked at the second most frequent word, okay, at that time it was he, okay, then the frequency would be roughly, the number of times it would occur would be roughly n divided by 2. Okay, so if this was the most frequent, this was the second most frequently occurring word. Okay? And then you looked at the third most frequently occurring word, and whatever it was, it occurred roughly, what would you guess, how many times? n over 3. You looked at the fourth most frequently occurring word, occurred roughly n over 4, and so on. Okay? Now, Zipf was not the first to observe this kind of distribution, but he's the one who popularized it, and maybe he may have been the first one to notice it in this particular context. Okay, so that's something that was very funny. It was a completely different kind of phenomenon. Now you could ask, well, where else does something like this occur? And something like the Zipf distribution also occurs in terms of populations of cities. Okay, so if you look at the most populated city, the largest city in the United States, that's probably New York. And it has a population of about 8 million. And then you look at the second most populated city, and that's probably LA, and that's about 3.8 million. Look at the third largest city, and that's Chicago. What would you guess? Yeah, it's about 2.6 or 2.7 million. So it's not quite, but you follow it out, you put it on a log scale, you see a straight line. You see a few bumps here and there, but roughly it's on a straight line. Yeah, it's going to eyes, okay. Yeah. So okay, well, if it happens in 2 contexts, you could say, well, it's a coincidence. If it happens in 3, then you say it's a law. Oh my goodness, I shouldn't have done that. I see now why we had all those things. Okay, so we'll get to it later. So okay, I'm going to make this lecture as short as I need to use only the available blackboards. Okay, so so here's a third context where it shows up is in terms of incomes. Okay. Again, if you look at the income distribution, it roughly follows this kind of a distribution. The highest earning individual earns roughly twice as much as the second highest earning individual, roughly 3 times as much as the third highest, and so on. Right? Okay? So, well, these are called the Zipf distribution, but actually for income, the distribution is actually slightly more complicated, and that's where these power law distributions come up. Okay, so what are these power law distributions? Well, in fact, for incomes, the distribution, the kind of distribution was actually put forth by the economist Pareto, and so Pareto's law was something like this. So he suggested that the probability, if you look at a population of n people, and you pick one at random, and you want to know what's the probability that the income of that person is greater than X. Okay? Well, then this is D. It goes as D divided by X to the power of alpha minus 1, where D is some constant. Right? D just depends upon the parameters at large. Okay? So if you want to know what's, so this is the probability. So you have n individuals in this population, and you pick one of them at random and you ask them, what's, is your income greater than X? Pick any X that you want. Then Pareto said, well, this is how incomes sort of, this is the law that incomes follow. So let's see what this tells us about, how the incomes fall off. If the highest earning person has income, say, A, then what about the second one? Is it A over 2? Or how does it actually fall off? Okay, so let's try to figure this out. Okay, so if the probability that the income is greater than X equal to D over X to the alpha minus 1, let's figure out how many people have income greater than X. So number of people. So in fact, okay, let's figure out what this is. This is, the probability is the number of people with income greater than X divided by n. This is D divided by X to the alpha minus 1. Right? Okay. So now, well, of course, you could move this n across to there, and so you say the number of people with income greater than X is ND divided by X to the alpha minus 1. Okay? So from this, can you figure out what's the income of the highest, the rough income of the highest, the person with the highest income? Right? What's the highest income among these n people? Well, you want to find out that x such that the number of people with income greater than x is exactly 1. Right? So you solve for this equal to 1. Right? So highest income equal to x such that nd divided by x to the alpha minus 1 equal to 1. So x equal to nd raised to power of 1 over 1 plus 1 over alpha minus 1. Okay? Is that okay? Okay. Now suppose we wish to figure out what's the income of the ith, what's the ith biggest income? What's the second biggest income or the third biggest income? Right? So let's figure it out for general I. What's the ith largest income? Okay, so ith largest income equal to x such that what? nd divided by x to the alpha minus 1 equal to I. Right? So what's this x? Well, we do the same thing. It would be x would be nd divided by I whole raised to the power of 1 over alpha minus 1. Okay? So, yeah. I'm sorry? Alpha is a parameter. Alpha is a constant. So we'll figure out what alpha should be, right? So alpha is just some constant here. Okay? So now can we simplify this further? Well, we can say that the numerator here, nd to the 1 over 1 alpha minus 1, this is the income of the highest person. Right? So this is, let's call it I sub 1. That's the highest income. Right? It's this much. Right? Divided by I to the 1 over alpha minus 1. Okay? So what's this telling us? It's telling us I sub I, so the ith largest income is I sub 1, the highest income, divided by I to the power of 1 over alpha minus 1. Okay? So let's call 1 over alpha minus 1 equal to beta. Right? It's just a constant, right? Alpha was a constant, so beta is a constant. And so the ith largest income is the largest income divided by I to the beta. Right? If we had beta equal to 1, this is exactly like Zipf's law. Right? He would say, what's the second largest income? Well, it's the highest income divided by 2. Right? So if you have beta equal to 1, then I sub 2 equal to I1 divided by 2, I sub 3 equal to I1 divided by 3, etc. Right? It's Zipf's law. Okay? But if beta is different from 1, then you get something very much like Zipf's law, but except with a slightly different exponent here. Instead of divided by I, you divide by I to some power. It could be square root of I, it could be I squared, it could be I to the 1.5 or 0.92, something like that. And so what you would do is actually, you'd figure out empirically what this value beta is. That gives you a general power law distribution. So Zipf's law is a particular case of a power law distribution where beta happened to be equal to 1. Yeah? This make sense? Okay, so now let's try to contrast these power law distributions from distributions that we've already seen so far, right? By the way, okay, so where do these distributions show up? They show up not only in populations of cities and word frequencies, incomes, but they also show in popularities of websites. How many, if you look at the degrees of the web graph, so you say, well, how many websites point to a given website, right? This is an important metric, right? It says how popular is a particular website. Right? This is an extremely important thing that websites try to optimize. Well, then that follows a power law distribution. Okay. Actually, another thing that follows a power law distribution is citations. So if you ever write a paper and you want to know how many people cite it, it follows a power law distribution. Okay. So the informal way of referring to this phenomenon is that the rich get richer. Okay, the fact that the richest person, earns twice as much as the second richest, who earns twice as much as the third richest, and 3 times as much as the third richest, and so on. The paper that cited the most tends to have twice as many citations as the one that's second most. And the third most cited paper has 1/3 as many as the most cited. I mean, why would it be like this? Why is reality like this? Okay, so we'll try to understand this phenomenon a little bit today. Okay, and again, the reason that this is so interesting is because when you look at distributions that come up so in the social sciences, in the biological sciences, and increasingly in anything touched by technology, frequently you see these power law distributions. And so this is why these are extremely important. Okay? But then the other thing that makes them very important is that they are nothing at all like the distributions we've seen so far. So let's go over the distributions that we've actually studied so far. So what are the distributions we've looked at so far? There's a binomial distribution, which looks like this. So there's k and the probability x equal to k, and it goes like this, right? Okay, so it's something like okay, I should have done a better job of it. It's not really, it should sort of go up very gradually here and then go up more quickly. And then you have the normal distribution, which is sort of the continuous analog of this, right? So this is probability x equal to k is n choose k, p to the k, 1 minus p to the n minus k. Okay. So the expected value is n times p, the variance is n times p times 1 minus p. Okay. Sigma is square root np 1 minus p. Then you have the normal distribution, which is sort of the continuous analog of this, where where we think of 0 as being there, and then we have roughly the same shape, except it goes out to infinity. Okay, and if it's a standard normal, then we have sigma expected value is 0 and sigma equal to 1. Right? Now, the important thing here in both these cases is as you go out from the mean, the probability falls off exponentially. Right? The probability distribution falls off exponentially as you go away far from the mean. And so this is what gives you this concentration around the mean. Now there's a third distribution that we looked at, which was Poisson, how many of you feel comfortable with the Poisson distribution? Yeah, well, good. It's okay to raise your hands. It's really okay to say you like Poisson distributions. How many feel completely uncomfortable with the Poisson distribution? Yeah, okay. Let me try to tell you why you should. Okay, here's a way to think about the Poisson distribution, which should make you comfortable with it. Okay, so what's the Poisson distribution? So take the binomial distribution. Okay, so let's write out this binomial distribution, and let's think of, okay, this is n, this is 0, right? You have n coin flips. The number of coin flips goes from 0 to n. But now let's say that the probability of heads becomes small. Okay, if p is small, well then the distribution sort of looks like this. Okay, so it's sort of roughly, if you wanted to plot the outlines, right? It sort of goes up very, very steeply, and then it tails off slowly in that direction, right? Because p is small, so n times p is out here, and n times p is very close to 0, right? And now, what you do is, in the Poisson distribution, it's really this picture, except you let n tend to infinity, and you let n times p be a constant. Right? So the Poisson distribution is exactly this distribution where this is lambda, that's your constant, and you exactly have this sort of behavior, right? So it exactly looks like this, except of course you have, this is all your integer points, positive integer points, right? And so the Poisson distribution is exactly the binomial distribution, except, and all your formulas look exactly like this, except you take the limit as n tends to infinity, so the formula becomes much simpler than this. So the Poisson distribution is a simplified version of the binomial distribution, right? Where the mean is constant and the number of coin flips tends to infinity. Right? And so now if you write out the probability x equal to k is lambda to the k over k factorial e to the minus lambda. The expected value of x is lambda, and the variance of x is also lambda. Okay, so lambda takes the form of n times p. Right? It's the expected number of heads. Right? So the Poisson distribution is sort of the same thing as the binomial distribution, except that you simplify it. Right? You make it, you choose parameters so that so it's a very biased, it's one where p is very, very small, right? The chance of heads is extremely small, but the expected number of heads is a constant, right? So it's this very biased picture where you're going, instead of peaking in the middle, you're peaking all the way towards the left. And then, because you're letting n tend to infinity, all your formulae simplify a lot. So the Poisson distribution is much easier to work with than the binomial distribution because the formulae are so much simpler. But again, the main point is the Poisson distribution is no different than the binomial or the normal distribution. It peaks very sharply in the middle, and then it falls off very, very quickly. It falls exponentially fast as you go away from the middle. Okay, those are most of the distributions we had. Were there any other distributions we looked at? Oh yeah, there was geometric and exponential. In fact, geometric and exponential are more or less the same thing, right? One is the continuous analog of the other. So the geometric was just the waiting time for heads. And what did it look like? So in the geometric distribution, we had the probability x equal to k was 1 minus p to the k minus 1 times p, right? So you had k minus 1 tails followed by heads. Expected value of x was 1 over p, and variance was 1 minus p over p squared, something like that. Was it 1 minus p over 2 times 1 minus p over p squared? Right? Maybe. Okay, so if you were plotting out the geometric distribution, it just looked like this, right? It was right. You just had this exponential decay like this, right? Again, there's an exponential decay, just like that. And of course, in the case of the exponential distribution, your probability density function really is exponential, right? It's f of x was lambda e to the minus lambda x, right? With expected value 1 over lambda and variance 1 over lambda squared. Okay, so again, you see these exponential fall off here and here, right? What about the power law distributions? How does that fall off? Right? It doesn't fall off exponentially. In fact, we talked about how it falls off. It falls off as 1 over I, or 1 over I to some power, right? So Zipf, it goes like this, right? It's 1 half, 1 over 3, 1 over 4, 1 over 5, right? It doesn't fall off very quickly at all. Okay, so here was, there was an article in the Atlantic Monthly, which was trying to explain Zipf's law, power law distributions to the lay person, to the common reader. And they were trying to explain it in the context of income inequality, right? So they were saying, well, incomes follow a power law distribution, and they were trying to say this is really bad. Okay, so because it means that there's an extreme amount of inequality in income. So they were trying to illustrate this point, and the way they wanted to illustrate this point was they said, well, look at how the heights of people are arranged. Well, the average height is whatever it is, 5'10", whatever it is. But then, the heights are concentrated very closely around that number, right? The chance that you are, you're off by a factor of 2. That's really 0, right? The chance that you see somebody who is instead of 5 feet 10, somebody is something like 11 feet tall. Well, where do you find such a person? So they said, well, let's imagine. Okay, so So let's imagine that heights were distributed according to this power law, the same power law that incomes are distributed according to. And they came up with some numbers, and they said, well, what's the number of people who would be, in the U.S., who, take the same average height, but now imagine that we had a power law distribution. Well, then they said that there'd be about 60,000 people whose heights would be above 11 feet. Okay? There'd be about 10,000 people whose heights would be as tall as giraffes. There'd be at least one person who'd be as tall as the Empire State Building. And there'd be 180 million people who would be under 17 centimeters tall. Okay? So it's quite remarkable what this power law distribution looks like and how different it is, right? So we are typically used to these distributions, right? The kinds of things that we usually look at, they're like this. But then once you go into these other contexts, like sizes of cities or income distribution, but then also almost all parameters related to the internet. Right? The internet graph or the web graph, both of them have power law distributions, meaning the degrees of vertices and, on the actual internet or on the web graph. Both satisfy a power law distribution. Okay, so any questions? Yes.
It seems like, just thinking about this, the Poisson distribution and the binomial distribution both work better for whole populations, but then you've been applying the power distribution to the same idea as height. So could you apply an exponential power distribution to the end of a normal curve? Like if this is your bell curve, could you analyze like the extremes in a power function?
Oh, no. Yeah, so you're asking whether the extremes of a normal distribution might look like a power law distribution. And the answer is no, it doesn't, actually. So even if you look at the extremes, it's still falling off exponentially. And it turns out the power law distribution, it has many properties, including the fact that it's scale invariant. So in other words, what you can do is you can sort of narrow in on the power law distribution, and it still looks like a power law. So basically, if you change the scale at which you are working, you let x change to constant times x, and now you ask, what distribution do you get? Right? How do you write the distribution again? And the answer is you get back exactly the same distribution except scaled. Right? Whereas on these distributions, if you change the scale, they don't look the same. Okay? And in fact, what you can show is that the power law distribution is the only distribution which has this property that it's scale invariant. So it's really a more intrinsic property of the distribution. Yes?
It seems like the Zipf law is, for power distributions are much less steep. So shouldn't they be better for incomes? Of course, they're centered around a different part. They're not centered around the average.
Yeah, so you see the thing is, it depends upon what you might be looking for. So in terms of incomes, in terms of income equality, you could look at two different kinds of places that you might think of. One is where the income distribution sort of looks like that. That's the average income. And that's, say that's zero, and that's average, and that's infinity, and so on, right? And a Zipf's law wouldn't look like that, right? In a Zipf's law, you might have something which looks So how does it go? The probability the income is greater than x goes as d divided by x to the alpha minus 1. What's alpha? So beta equal to 1, right? If beta equal to 1, what's alpha? It's 2, isn't it? So alpha is it 2? Okay, so d divided by x, right? So it goes as 1 over x, right? And it's falling off as 1 divided by x, which probably goes like that. Right? So instead of going down exponentially like this, it's going, so instead of going sort of like that, it's sort of gently going down. And that's what, so it's, these power law distributions are also called heavy tail distributions. Because if you look at the weight of the tail, it's actually pretty large. Whereas if you look in these kinds of distributions and you look at what's the weight of the tail, it's almost 0. Right? The tail is negligible here, whereas the tail there is pretty large. Yeah? Yeah.
Would the spread in Zipf distribution be much greater than the spread in like normal?
Oh yeah. So you're asking what's the variance? Is the variance much larger here? In fact, for these power law distributions, for certain parameters of, depending upon what alpha is, if you let the domain tend to infinity, then the expectation may not be defined, or for certain values of alpha, if alpha is small enough, then the variance may become infinitely large, or it blows up. As the point is that the variance in those cases is tiny, and here it's very large. And for certain parameters of alpha, it may even tend to infinity. Okay. Yeah. The median versus the mean. So in the power law distribution. Oh yeah, that's right. The mean is much higher, yes, than the median. Yeah. More questions? Okay, so far I've just been describing the power law distributions as a phenomenon. Okay, so what we'll do is we'll take a 2-minute break, and then I'll describe to you how they come about. So I'll describe to you a very simple model that leads to a power law distribution. And this is one of the main ways that a power law distribution comes about. Okay, so whenever you see this activity, you sort of suspect that there's going to be a power law distribution. Right? No, it's okay. No. I think I'll just. I don't need more than 1 or 2 boards. So. Okay. So let's talk about how these power law distributions come into being. So what is it that makes them happen? Okay, and so one of the characteristics that make power law distributions appear is human activity. So what is it about human activity that causes power law distributions to occur? Okay. So it turns out that there are, well, one can say various factors, but they really boil down to two different ideas. Okay, so here's the one way that they come about, and I'll list three different things that come under that rubric, and if you think about it, they actually are the same phenomenon. So the first thing is size-independent growth. Okay, so what do we mean by size-independent growth? So let's say that everybody's income is whatever it is today, okay, and then every year their income changes by a certain random amount, okay, according to some random variable, which is proportional to whatever their income is today. Okay, so if their income today is X, then there's some random variable which says how much of an increment they get. Okay, so let's say that they get Y amount of increment, okay, per unit of income that they have today. So Y is going to be a random variable for each one of them independently. Each person independently has some increase in income, except that the new income is X plus Y times X. Okay? So Y is sort of the percentage increase in the income. So say each person, for each person what we do is roll a 100-side, a very large die, and it comes up 0.5% or 5% or 2%, okay, according to some probability distribution. That's what Y is, and then if it's 2%, then the new income is 2% higher compared to what it was last time. Okay, but the increase in income doesn't depend upon their income, right? So if you could have a different way of formula according to which income increases, where the higher your income is, the less it might increase. The lower it is, the more variable. But that would lead to a different distribution. This is completely independent of what it is today, right? Whatever it is today, you get a certain percentage increase, which is itself a random variable. So if you have different people distribute, who have different incomes, and each of them is now fluctuating randomly, you get you get this kind of a power law distribution. Okay. Second way this happens is through another, is through an extremely human activity, which you can describe as imitation or copying. Okay. So how does this happen? How does imitation or copying lead to a Zipf distribution? So you remember I told you that the number of citations of articles follows a Zipf distribution. So now, why would it be that the rich get richer in terms of citations? If a document is highly cited, then the number of citations tend to grow much quicker than something that has low number of citations. Well, the point is, when you're looking for a document, when you're looking for an article, things that are not cited, you're unlikely to even find them. Right? So the highly cited articles, there are many, many ways that you find them. And then it's more likely that you'll cite that article. Okay, that's one way that articles get cited more, the more they are cited. Another way they get cited more, the more they are cited, is because, if you cite, typically the number of articles that are cited at the end of a paper, not all of them have been read. So what are you looking for at the end of the paper? You're sort of saying, well, such and such is known to everybody. Well, of course you know it, but you didn't go and actually read the paper. But you know that, you just look up what is the standard reference to cite, and so that particular paper gets cited more and more. Right? So it's through actually copying. You look at what was cited, and you copy that thing down because you know that it actually leads to the correct thing. Right? Maybe there's another paper which is equally good at saying what this one did, but you just didn't find it. Right? So that's the second way that power law distributions come about. And the third way is called preferential attachment. Which, okay, again, it should be the same thing. So let's see. Again, preferential attachment, in terms of websites, the more links a website has, the more chances the next time you're trying, it's going to be linked to. Right? So, a document with many web links is considered more important. So it's really more or less this same sort of idea. Okay? Well, let me give you another example of imitation to make it different from preferential attachment. Maybe cities. Right? So why is it that the largest cities twice as large as the second largest city? So where's the imitation or preferential attachment coming in there? I'm sorry? Migration, yeah. So why would you tend to go to a city which is larger? Well, there's jobs, there's also the fact that people like to hang out together, right? So the bigger the city is, the more likely you have friends there, right? And then you go to that city because you're twice as likely to have friends there as the second biggest city, and so on. So suddenly the same sort of imitation or copying. Somebody else went there, and then you decide to go there too because they were doing well there, they're happy there. Why don't you follow them? Right, so it's the same sort of. So all these are extremely human sort of activities, and they lead to these power law distributions. There's one more sort of very different kind of reason why you get power law distributions, which is when you have a trade-off between two different things. right? So when you're trying to balance a couple of different factors. So for instance, let's say that you're creating a network, a communication network, and each person, so you have some sort of a network. There are nodes, and now one way you get a power law distribution in the degrees of this network. So so some of these nodes have very high degree, others have low degree, and so on. If you look at the highest degree node, it'll have maybe twice as much as the second highest degree, and so on, or whatever beta or alpha happens to be. Now, one way this comes about is because maybe what happens is the way this network was created. When you want to attach a new node, one way you could do it is you could say, well, let me find the node that's closest to the one that I want to add, and I'm going to add a link to that. Right? That's one way you could add in the new node. That won't necessarily lead to a power law distribution. What leads to a power law distribution is if you think to yourself, look, I want to go to some place which is closest to where I'm starting from, but I also care about how close I am to a central location. Right? So maybe, so possibly this is what the network looks like, and you're coming in here, and you think to yourself, well, look, I could add myself at the end of this like that. And that's the closest. That's the least costly way for me to attach myself to the network. But on the other hand, I'm going to pay forever because my latency is going to be very large. So better than that, better than just minimizing the cost now, I should look at the trade-off between the cost now versus performance later. And so now, instead of optimizing just one thing, you're optimizing a trade-off between two things. You're trying to say, well, instead of doing this, let me maybe do that, because even though it's a longer link, it optimizes some sort of linear combination of how much I have to pay now versus what kind of latency I actually achieve. And when you do this, you get a power law distribution. Okay? So these are all things that lead to power law distributions. Now, what I'll do now, what we'll do next, is we're going to look at a very simple model of this phenomenon. And it's a very simple, very elegant model of this, and we'll show that it leads to a power law distribution. Okay, that it leads to, instead of leading to concentration, it leads to this kind of distribution which is much more relaxed. Right? It's a heavy-tail distribution. And so what we'll study is what's called the Polya urn model. Okay? So in this Polya urn model, we imagine. Okay, so there are two ways of saying it. Let me say it each of the two ways. So we imagine it's like this. There's an urn which initially has one white and one black ball. Okay, so that's what it contains initially. And now what you do is I don't like this way of describing. Let me describe it in a different way. Let's describe it as two different urns. Okay, so you have two different urns, each of which initially has one ball in it. Okay, and now what you're going to do is you're going to throw in n more balls into these urns. Now, if you were going to throw in just normal, standard, normal balls in there, well, each one goes into each urn with probability 50%, And so after you throw in these n balls, you'll get this sharply concentrated, the number of balls in urn number 1 will be roughly n over 2, and the number in urn number 2 will be roughly n over 2 with these sharp concentrations, plus minus square root of n, as we expect. Okay, but we're going to change the process a little bit. And we're going to throw in this imitation, copying, preferential attachment, whatever you want to talk about. So what we'll do is we'll say, well, these balls are somewhat magnetic. And so when you throw it in, if at that point there happen to be, K balls in this urn and L balls in this urn, then the next ball that you throw in, it goes into this urn with probability K over K plus L. Right? Because it's magnetic. If there are a lot of balls here, it gets attracted to this side. Okay? So it goes in here with probability K divided by K plus L, and it goes in here with probability L divided by K plus L. Okay? So instead of just throwing them in independently, now we are doing a little bit of copying when we throw in these balls. Now we want to know what's the distribution of the balls at the end of this process. How many balls do we have in each urn? So if you think of n, if n was 1,000,000, what's the chance that you throw only 100,000 balls into this one and 900,000 into that one? Okay. Well, without this preferential attachment or copying, the chance would be essentially 0. Right? You throw 1,000,000 balls at random into these two urns. You expect 500,000 in each. Your standard deviation is around 500 or 250, something like that. Right? The chance that you throw, you're off by a few 100,000 is basically 0. Right? That's your sharp concentration result. What would you guess the answer is here? What's the chance that you get fewer than 100,000 in the first urn and at least 900,000 in the second one? Turns out it's about 10%. Okay. So you get this, just the fact that you're doing preferential attachment leads to this, instead of this real concentration, it leads to this large disparity. Okay? So actually what happens is that the number of balls that you throw into each urn, it's uniformly distributed. Right? So the probability that m balls end up in urn number 1 is exactly m over n. Right? It's completely uniform distribution. Right? The chance that you end up with exactly, 0 of these n balls here is exactly the same as the chance you end up with n over 2, is exactly the same as the chance you end up with n. It doesn't matter what the number is, it's completely uniform. Oh, it's 1 over n. Right? The chance that at most m balls end up in urn number 1 would have been m over n. Right? The chance that exactly m balls end up is 1 over n. So every possibility is equally likely. Okay, so how do you suppose one would show something like this? So it turns out there are two ways of doing it. In your homework, it shows you how to how to do some calculations which would, if you take them a few steps further, would actually lead to this result. But, it's a little bit involved, but not so much. It turns out there's a way of figuring this out which is just pure magic. Okay, it's incredibly clever. Okay? Polya was a very clever man. Okay? So here's how we think about it. Okay, so let's do this. Let's suppose that we have n plus 1 balls, and they are labeled. Okay, so there's ball number. Okay, this is number 0. This is number 1, 2, up to n. Okay, and what we're going to do is we're going to take these n plus 1 balls and we're going to permute them at random. Okay, so we reorder them so that they occur in completely random order. Okay, well, you can, if there are n plus 1 balls, you know how many ways there are to order them. There are exactly n plus 1 factorial many ways of ordering them. So we pick one of these n plus 1 factorial ways at random. Okay, so let's go ahead and reorder. So this might be number, 50. That might be n. That might be something else, so on, right? And somewhere here is ball number 0. Okay. Okay. So what we claim is, after you do this reordering and you look at how many ended up to the left and how many ended up to the right, you could think of this as the left turn and this as the right turn, and you'd get exactly the correct distribution, right? So if you just do this reordering at random, and you ask how many ended up to the left of, this is ball number 0, how many balls ended up to the left of ball number 0 versus how many ended up to the right, this is exactly as though we had the Polya urn process, where we were throwing in balls at random and they were being magnetically attracted one way or the other. So the chance that we saw exactly, 50 balls end up to the left in this process is exactly the same as the chance that 50 balls ended up in the left bin. 50 of these n balls ended up in the left bin. Okay? Is it clear what I'm claiming? It shouldn't be clear to you why I'm claiming this, but at least what I'm claiming. Is that clear? It seems like it should have nothing whatsoever to do with this, right? Why should these two processes be the same? But we are going to claim that these two processes are exactly the same. Let me say once again what the two processes are. So here, we started with 1 ball in each urn, right? And now we are throwing n more balls. Okay? The balls are magnetic. So initially, the first ball you throw in, it has equal chance of going here or here. Now, after you throw in the first ball, let's say it went into this one. Now, the next ball, ball number 2, is twice as likely to go in here as here. So it has 2/3 probability here, 1/3 here. Okay? Let's say it went in here. Now the fourth ball, the third ball, has chance 3/4 of going in here and 1/4 of going in there. Right? If it ended up there, the fifth ball has chance 3/5, 2/5, right? That's how it keeps going. So the chances keep changing every time, depending upon how many balls ended up here, how many ended up there. Right? Very complicated process. We want to know how many balls ended up here at the end of the whole process. Right? It seems impossible. It seems like, who could answer this question? And then the claim is, no, it's actually something it's very simple. There's a completely different process which has the same answer. And this other process is very, very simple. So what you do, you take n plus 1 balls, each numbered 0 through n. Okay? Now you go ahead and jumble up the order completely. And you see where ball number 0 ended up. Okay? And you say, how many balls ended up on the left of it? Well, think of those as the ones that ended up here. How many ended up to the right of it? Think of those as ended up here. And the answer is same, it's the same answer. Those are the probabilities. So now, once you know that's the probability, what can you say about the number that ended up on the left? Right? So, well, these balls were jumbled up completely at random. In particular, the position of the zero ball is completely random. Right? It has equal chance of ending up here, as here, as here, as here. Right? Which means the chance of every possible answer here, of how many ended up to the left, is equal. Right? So how many possibilities were there? Well, it could be anything from 0 to n, so there are n plus 1 possibilities. So it was 1 over n plus 1. Okay, so it's completely uniform. Okay, so how do we see this? Well, we see it exactly the same way. So you see, so how does this process start off? Well, this process starts off. Here's another way that you can rearrange these balls at random. What you can do is you can start with the ball number 0 out here. Okay, and now where should you put ball number 1? Well, if you're going to make up a random ordering, it goes either to the left or to the right with equal probability. Okay, so go ahead and put it to the left or the right. Okay? What's that like? That's like taking the first ball here and you put it either here or here with equal probability. Okay? But now, if ball number 1 went to the left here, now where do you put ball number 2? If you're going to jumble up the order completely at random, ball number 2 can go either here or here or here. Right? So there are 3 possibilities for ball number 2. 2 of them are to the left of 0, and 1 is to the right. Okay? The same magnetic property we wanted here. Okay? Okay, so now suppose that ball number 2 also ended up here, to the left. Now what happens? Where do we put ball number 3? So this is ball number 1, this is ball number 2, ended up on the left. Where should we put ball number 3? Well, it can go either here, or here, or here, or here. Okay. How many ways are there to put it on the right? Only 1. To the left, 1, 2, 3. Okay? Exactly the magnetic property we had here. So suppose ball number 3 goes there. Now how many ways are there to place ball number 4? Well, again, we are jumbling it up completely, right? So 4 can go either here, 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 or here. Right? Okay, so 2 ways of putting it to the right, 3 ways to the left. Exactly what we want here, right? So this was ball number 3. So the next ball should go here with probability 3/5, here with probability 2/5. Exactly what we get here. Right? So the 2 processes are exactly the same. So they have the same answer. Right? Yes?
I'm wondering how this would be affected, how much this is affected by the starting conditions.
Oh, very good. Yeah, so let's look at that. Oh, no, maybe you want to answer that. Yes.
Well, I'm not going to answer that, but I'll just elaborate. You start with 1 ball in each way, you start with 1,000 balls.
Oh, yeah, good. What if you started with 3 in this one and 2 in this one? What do you expect in the end?
Expect more in the left one.
Yeah, because the rich get richer. Right, so you expect at the end for this to be, 3 over 2 times as large as that. Right, that's this rich gets richer phenomenon. this is okay. So this is the phenomenon. This is the early starter phenomenon. If you're going to, if you plan to do a startup, do it early because that's how it grows. Okay, this is the phenomenon. So, okay, so. So let's examine this more general condition. Okay, so now suppose you start off with K in this bin and L in that bin. How do we analyze that case? Well, let's do something slightly different. Let's actually analyze the case where instead of 2 bins, we actually started with K plus L bins, each with 1 ball in it. Right? So suppose we start with a large number of bins. Actually, let's start with K bins. Okay. So let's think of K as L1 plus L2, where L1 is the number of balls here, L2 is the number of balls here. And now, if we analyze this case, then later we can sort of blur our eyes and think of the first L1 bins as bin number 1 and the last L2 bins as bin number 2, and then we'll answer that question. Right? So is everyone convinced that this question contains that question? So if we solve this one, we've solved that one. Okay? But now, can't we solve this one? I mean, what was special about the 0 ball? It was just a... What's it you call this? Stars and bars, something like that? What was it? There's some name for it. Well, anybody... I'm sorry? No, not ball. This is that other thing. Stars and bars. Okay, it's stars and bars. Okay, good. So it's the same thing here, right? So this ball is the bar, right? Is that what it is? It's what defines the box. Okay, so here we had 2 boxes, so we had only 1 of these. We need K boxes, so we need K minus 1 of these guys. Right? Okay, so let's just think of it like this. We have K minus 1 red balls and N white balls. Okay, these are your bars, these are your stars, right? And you now go ahead and rearrange these. So you start with the K minus 1. So these are your K minus 1. Okay. Maybe these were not. Let's say these were the K minus 1 you started with. And now, the first ball you put in, you can either place it here, 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 or here. So there are exactly K places you can put it. And then after you place it somewhere, there are exactly K plus 1 places, and so on and so on. And you get the same magnetic property as before. And then what can you say about the expected size of each of these bins at the end of the day? How many balls do you expect in each one? So there are K boxes, K urns, N balls. The expected number in each one would be, N over K. Actually, how do you see that? How do you see that it's N over K? How do you know that these end bins are not special? Maybe there's an end effect, and right? Maybe there are more ways of placing balls here or fewer ways of placing balls here. How do you know they're all the same? See, what you could do is instead of putting it in a line like this, you could sort of fold it around and put it in a circle. So if you fold it into a circle, you'd actually be placing one more ball. Right? So if there are 1, 2, 3, 4, 5 here, when you put it into a circle, you'd have 1, 2, 3, 4, 5, 6. Right? Where if this is how you had it before, where this, that's how it was, and now you close it with one extra such red ball. Right? And so these are your two intervals on the two sides. But now you have complete symmetry. Right? Everything looks the same as every other because it's all on a circle. You can't tell the difference between this and this. Right? So the expected value of each one is the same. But the sum of the expected values is how much? The expected value of the sum is n. Right? The expected sum of the lengths of the intervals is n. So each one must be n over k. Right? Linearity of expectations. Okay? And so, how many do you expect in this one? Well, this is exactly L1 of those k intervals. So you get L1 times n over k. And this one would be L2 times n over k. Okay? Now, you can also you can also do a back of the envelope calculation, and you can figure out, well, that's the expected value, but what about the biggest one? How big do you expect it to be? It turns out the biggest one you expect it to be not much larger than n over k. You can show the largest is going to be n times log n over k. Okay, this is an exercise, if you do a back of the envelope calculation. And if you look at the smallest, again, if you do you have to do some approximations, but if you do it, you'll see that the smallest one is n over k squared. And this is where you see the power law distribution coming up. The kth smallest is n over k squared. It's 1 over k times the largest. Okay, and that's your power law distribution. Okay, let's stop here and